Welcome. Today's lesson is entitled Introduction to Exponential Functions. As you see on your notes worksheet, we're going to do a couple investigations to develop our exponential model. They're a little contrived in nature, but they should be sufficient for our purposes. And then we'll do a couple good applications at the end of the lesson. So why don't we go ahead and start out investigation number 1 at the top there. You need a calculator to do a couple calculations with me. And so let me go ahead and read it. It says, suppose you deposit $1,000 into an account that earns 6% annual interest compounded annually, meaning that the interest is just paid once at the end of the year. 2 parts to number 1 here. Determine the balance of the account after 1 year and how much interest was earned during the first year. Perfect. So let's see what we want to do with this. It looks like if we're going to figure out the balance at the end of the year, we want to include the $1,000 that we started with. So everyone, if you would, write the 1,000 right up above there. And what's going to happen at the end of the year is we're going to earn 6% of that 1,000. So we're going to add 6% of the $1,000. And that's a good start. If I did this calculation right here, I would be able to get the balance in the account at the end of the first year. Perfect. But what I want to do is just write this calculation in a slightly more efficient manner. So here's what I'm thinking. And bear with me on this for just 1 minute. I'm going to rewrite this part in just a little bit here. Seems a little unnecessary, but watch where it's headed. I'm going to put the 1 out in front of the 1,000. And then I have obviously the 6% of the 1,000. So I haven't really changed anything. I'm just going to multiply that 1,000 by 1 there. That looks great. And this is an algebraic expression that we're able to manipulate a little bit here. I have 2 terms, this one and this one, separated by that plus right in the middle. And I notice in each of those terms is 1,000. So what I'm going to do is that great little technique of factoring. I'm going to factor out the 1,000 from each of those terms. And when I do, I'm going to create my parentheses. Notice I have the explicit 1 right there. I have the plus right in the middle. And from this term, of course, after I factor out 1,000, I have 0.06. Very nice. Again, this expression is the exact same as what you see up above. Again, a little better. Let's go one last step here. There's my 1,000. And I hope you would all agree that I can combine those together numerically. 1 plus 0.06 is 1.06. And so as a result, this calculation is exactly the same as what I started with up here. I would argue this is a little more efficient and probably a little more necessary for where we're headed. Okay, so let's go ahead and get this going. So how about just write balance and the interest earned there. I'll just write interest. And let's see what we've got going on. If I do the 1,000 plus 0.06 times 1,000, let's go ahead and bring the calculator up and pull that off. Here's my 1,000, 0.06 times the 1,000. And of course I get that right there. There's my balance. And again, just wanted to show you that, of course, this is the calculation I'd prefer us to do. And you'll notice, of course, we get the exact same answer. So take the original and multiply it by 1.06. I like that. Keep that in mind if you would. Okay, well, let's get a couple things going. I saw the balance was $1,060. That's perfect. And which means, of course, that we earned $60 over the course of the year. Wonderful. Okay, looking good. We'll develop a couple things for the next year here. Obviously, number 2, determine the balance of the account after the second year and how much interest was earned during the second year. I guess I would ask you this before we even head into the calculation, the second part. Do you think we're going to earn $60 of interest during the second year? Do you think the interest earned is the same from year to year to year? Well, let's find out. So I'm going to go through it one more time, just all the way through. In this case, after the first year, we had $1,060, right? And the idea would be that we would add 6% of that $1,060 at the end of the year. So if we want the balance of the account, we started with this, and of course we add 6% of it at the end of the year. Now we'll get that calculation momentarily, but I hope you would all agree. I'm going to go a little further with this piece. Obviously this looks just like this up above, And if you remember, I wrote this like this right here. So I'm hoping you would be in agreement that I could really just take that 1060, and instead of writing this, it's a little simpler to do this right here. And that's probably the calculation that we'll put in the calculator momentarily, but I do want to go one step further and see it in relation to what we started with. I want it to always base it on the $1,000 here that we started with. And so where did this 1060 come from? Well, of course, the 1060 is this calculation right here. Hope everybody remembers that. So as a result, what's kind of interesting about this is in order to get the balance out of the second year, I did my 1,000 and multiplied it by 1.06. And then, as a matter of fact, now for the second year, I would take that number and multiply it by another 1.06. And you can start to see that I've multiplied it twice over by 1.06. Wow, we could even go one step further here and say that. Now we're going to do this calculation this way and this way so you can see it's the same. Perfect. All right, guys, let's get that calculator up. So second year, we started with the $1,060 there at the end of that first year. And now I get 6% of that 1,060. And there we go, 1123.60. Perfect. We'll write that in momentarily, but let's see what I wrote at the end there and see if it's the same. So what I said was, you know what, we can start with the 1,000. We multiplied it by 1.06 the first year, then multiplied it by another 1.06 the second year. What do you think, everybody? Should it work? Yeah. Let's put a little multiplication right in there. And we've got it. And notice we get the exact same number. Okay, so the balance was 1123.60. Let's get that in there if we could. Was the interest exactly $60 like the first year? No, it doesn't look that way. In this case, if you look at what we ended with compared to what we started with, it looks like we made $63.60 over the course of the year because we ended up taking 6% of a larger number. So our interest was more. Great. Hope everybody at least understands the basic calculations behind exponential models without actually even the development yet. Let's go ahead and do the third year and then we can start to put it together. So determine the balance of the account after the third year. All right, how much interest was earned. So let me just go through one last time in this piece. So after the second year, that's how much we had. And so after the third year, we would add 6% of that. And again, that is a calculation that we can do. But I don't want to have this number handy. I want it all in terms of the information given in the original problem. And so I hope you would be in agreement, just like the last time around, this, well, let's do this, the 123.60 times 1.06, of course. So this, obviously, we can make to look just like this right here. Hope that works for you. And what is that 1123.60? Where did we get that number? Well, if you remember, we got it from taking the original 1,000 times 1.06 the first year times 1.06 the second year. That gave us this. And now, of course, everybody, we're multiplying it by another 1.06. Wow, the math is actually really quite fascinating as you kind of look at it, because then it allows us to raise it just to the third power. And that's what we'll see. Okay. Well, again, let's do the calculation there just to get our values in place. And then just want to make sure you see that both will produce it. So, you know, this is what we had at the end of the second year. I'm going to add 6% of that. So let me just go ahead and type that in. If you could do the same, that would be great. And there we go, about 11.91. We'll round to the nearest cent there, so in 2 cents. If I wanted it just from the beginning, would this give us the same exact number? What do you think? And there we go. So you can see our calculations are working out beautifully, and this is a nice compact way to put it together, and I hope you see our exponential model probably unfold here. So the balance, of course, I think I saw 1191.02, give or take, which if we do a little subtraction just from that last one here, let me just take a quick peek. I'm getting about 67.42. You can correct me on that if need be. But let's go with that piece. Awesome. Will the interest continue to rise and rise and rise? Yeah, of course, because we're taking 6% of larger and larger numbers. Okay. And now I think we're ready to put it together. Number 4. Everyone put a little asterisk by it if you would. Determine the balance of the account after T years. And let's see if we can see our model in action. So you could do B for balance, and typically I kind of write it as A, so the amount, so to speak. So what do you think? What would be the balance after 10 years, 20 years, 40 years, whatever the case may be? Do we have to continue to do this calculation year after year after year, or can we come up with a nice simple model to put in a value for T? Well, I hope you saw that it looks like we started with the 1,000. That was the initial piece. And I continued to multiply by 1.06. And of course, repeated multiplication requires us to use an exponent. And so I multiplied by 1.06 the first year, the second year, the third year, however many number of years. And so as a result, you can see our exponential model here. The independent variable is the exponent. Wonderful. Okay. Well, that is the model that we would use for this particular problem. As you can see, this 1.06 showed up in the model. We'll definitely see this over the course of the unit, as a matter of fact. So 1.06 represents what we would call the growth rate. And conveniently enough, it says it for letter C, the growth rate is, and in this case, we got that growth rate by doing the 1 plus the 6%. And so in general terms, everybody, 1 plus R. So it grew by 6% per year, and so to get our growth rate, we did 1 plus the decimal representation of 6%, 0.06. What would your guess be in terms of exponential growth? So what do you think the interval is for this growth rate? I'm taking 1 and I'm adding the percent increase on it. Okay, well, and you're going to put a little b here for me. You'll see this b come up on the back side of your lesson here. But I hope you would agree that essentially b has to be bigger than 1. Obviously, if I'm adding some percentage increase to 1, that would make the overall number bigger than 1. And you see that obviously right here, bigger than 1. All right, keep that in mind if you would. We're going to do one more investigation and summarize it, put it all together. Investigation number 2. Suppose you buy a new car valued at $30,000. The car is expected to depreciate in value by 20% per year. Determine the value of the car after the first year and then after 2 years, etc. Again, I won't overplay it too much here. Hopefully just enough to see the model unfold. Okay, well, let's go for it. So watch the calculation, guys. You drive off the lot, it's worth $30,000. At the end of the year, the value of the car has gone down by 20%. We've lost 20% of this $30,000. So starts at $30,000, and then we lose 20%, which by the way is 0.2. We lose 20% of the $30,000. Hope that calculation makes pretty good sense. Now again, I'm going to manipulate this a little bit, just like I did for the first part of the last investigation. Can everyone throw a little 1 outside that 30,000? Good. So I start with 30,000. I'm going to take away 20% of that 30,000. Now again, see it in action, everyone. Factor out the 30,000. There's 1 here, and there's 1 in this term over here. So I take the 30,000 out, and I have a 1 from here, minus, and 0.2 from here. Wonderful. I think we've got some things going, working really well here. So how about 30,000? And instead of 1 minus 0.2, well, 1 minus 0.2 would be 0.8. Super. Well, I'm going to do that calculation from above and just make sure that it does coincide with this calculation right there. But it should, and I hope obviously that makes pretty good sense. So we start with 30,000, wrong investigation. And then we take away 20% of that 30,000. And so at the end of the year, the car is worth 24 grand. Perfect. Could I have done it in a slightly more efficient manner by just taking the 30,000 and multiplying it by 0.8 or 80%? Absolutely. And I hope that makes sense to you, because if the car has lost 20%, then it has retained 80%. And that's what you see there. Okay, long story short, let's go ahead and throw 24 grand right in there. So it lost $6,000 worth of its value. Do you think it's going to continue to lose $6,000 worth of its value? Nah, probably not. Okay, let's do the second year. One more time. Well, actually, we've got a third year coming, so 2 more times. So here's what I would do, of course. I would start saying from 1 year to the next, obviously $24,000, but we're going to now take away 20% of that $24,000, and that would give us our value. But, you know, really the question is, where did this come from? And, you know, what I'm thinking of is, let's see this piece right here. So let me just manipulate this a little bit more. I hope you would all agree at this stage that really I can take this and just write this as 24,000 times 0.8. That would be the case right there. You've got your 1 minus 0.2, so there's your 0.8. Now again, I don't really want to come at it from the 24,000 value. What I want to do is come at it from the $30,000 value. So let's see if we can tweak this a little bit right here and say, where did that $24,000 come from? Well, it came from this right here, of course. The way I got 24,000 was by taking 30,000, multiplying it by 0.8. That's this number right here. And as you can see, of course, I multiply it by another 0.8. What does repeated multiplication look like to you? Well, in this case, it would be squared, but we do use the exponent. And now, hopefully, after this time, it's really starting to come together for you. Let's go ahead and just do the calculation and get going on this. So, all right, let me get rid of this piece right here. There we go. Okay, so we've got the 30,000 times 0.8, and in this case squared. And so 19.2. Did it lose $6,000 this year? Nope. Less than that, because we're taking 80% of a smaller value. All right, let's go to the next one. Starting to come together, hopefully. So what did we have? 19,200. Sounds good. So we would do it one more time, guys. Bear with me. You can pull this off. So officially what we would do is take the 19,200, subtract 20% of that, and you could really start to see it come together. Really what that means is 19,200 times 0.8. There's that 0.8 showing its face again, but I don't want to do it from the 19.2. I want to do it from the 30. So what we said is, how did we get that 19,200? We multiplied it by 0.8 for the first year. We multiply it by 0.8 for the second year, and now for the third year as well. And it is really starting to manufacture itself. So let's go ahead and put that together. And that's my calculation right there. I multiply by 0.8 3 times over. Repeated multiplication uses our exponent. Let's get that last piece, and then I think we can come up with our model. Do a couple good applications at the end here. So 15,360 would be the total there. Cool. Now again, I don't want to have to go year by year by year. As you can see, that's a little time consuming. So the question is, could I just go ahead and write myself a model for any number of years, for T years? So the value of the car, again, do what you want. You can do an A again. or just a y equals or whatever you want there, but the value of the car, I'll go v. That's fine. Again, doesn't matter. And you can start to see the calculations, hopefully. So for any number of years, I would take my $30,000 and I would repeatedly multiply by 0.8 for however many years. And repeated multiplication is now my exponent. There's the model. So you can see that 0.8 right there for letter B. 0.8 represents what we would call the decay rate. Shouldn't come as a shocker, as the very next part deals with that. So the decay rate, how did we get that? Well, in this case, just be careful. Exponential decay is a little harder than exponential growth. So what we did for exponential decay here, we did our 1 minus 0.2. That's where we got our 0.8. And that 20% is what the car was depreciating in value by every year. And so as a result, this would be, instead of 1 plus r, like we saw in the last investigation, lo and behold, you see it's 1 minus r. Excellent. Okay. The interval for the decay rate, what do you think? So if you remember, for exponential growth, we saw that the growth rate had to be above 1. What do you think about this one? Well, as you'll see, it actually can't be negative. It has to be in between 0 and 1. And we'll actually explore that in a little detail, but our decay rate for all our exponential models will be between 0 and 1. And 0.8 obviously fits right in there. Okay, let's go ahead and summarize this. And hopefully the two investigations really make good sense, just calculation-wise. And now here is the exponential model, which will take over a good portion of our unit. So the exponential model, 4 parts, y, a, b, and x. And we saw all of those in play in the 2 investigations. So I'm just going to write the 2 off to the side here for just a moment. I'll probably erase it. You don't need to bother. But the first one was the 1,000 times 1.06 to the t. Okay, so we've got this one, and the other one was the 30,000 times 0.8 to the t. Okay, notice these 2 right here perfectly fit this generic model right here. That's the one we're going to use. So we have a, b, x, and y. Let's put this in play. And so everybody, if you would, a, I should say, represents the initial value, what we started with. So I hope you saw in each of the investigations, we started with $1,000 in the first one. The value of the car started at $30,000 in the second one. That's the initial value. That's what goes right here. Take a moment and see that piece if you would. All right, now everything we do, this unit will really revolve around the b value. So let's get that in play. And the b value represents either the growth or the decay rate, of course. So put that in. And how did we get that growth or decay rate? Well, if it was growth, it was 1 plus r. If it was decay, it was 1 minus r. So always just be very careful about that piece. Remember, r has to be expressed as a decimal, though. So in terms of 20%, we wouldn't do 1 minus 20. That wouldn't make any sense. So just make sure this is expressed as a decimal. In fact, I think I'm going to write that there. Always a good thing. Expressed as a decimal. Good thinking. Okay. Good. And let's just see. R, one more thing I have on my sheet. R is the percentage increase or decrease. So up by 6% gave us this. Down by 20% gave us that. There's our b value. Excellent. X represents, of course, the independent variable. For the most part here, not in every case, but really for the most part, exponential models, the independent variable will be the number of time periods, so over time. So I'm going to write it like this, but really it is just the independent variable. So hence I used my t instead of the generic x on that. And last but not least, the y, of course, represents the dependent variable. Typically, if we're talking about over time, this would be the amount of whatever we're looking at after however many time periods. Okay, so again, that's what we'll see it as. Okay, so independent variable, dependent variable, and again with exponential models, typically the independent is going to be time. All right, and that's what we see here, the amount or the balance over time and the value over time. All right, I hope it's all clicking at this point. I'm going to erase this piece. I don't think we need it anymore. And that's what we have. Why don't we do a couple good applications and round this out. Example 1. So according to the data that I researched, let's see, between 1950 and 2000, the population of Colorado increased by about 2.33% per year. In 1950, the population was 1 million and change. And so it says write an exponential model for the population. So in terms of the number of years since 1950, which is time. So P in terms of T. So there's our function notation, of course, P of T in terms of T right there. So what would be great is if actually you pause the video for a sec and try to write your own model. We have the initial value. We have the percent increase. Could you come up with the exponential model for this? Well, here's what I have. So population in terms of time, so P of T equals, and again, we have our initial value. Everything is going to stem from that. Now it says it increased by about 2.33% per year. Does it mean that it really actually for all 50 years increased by exactly 2.33% each and every year? No, but this is what is called an annualized increase. And so that's what we're going to use, 2.33%. Just underneath it or above it, wherever you want, I'm going to go ahead and write this as a decimal. So this would be 0.0233. I think that's the key there. And as a result, of course, for exponential growth, it's 1 plus that, so 1.0233 raised to the t. And there's your model. I hope everyone, based on what we've seen before, is comfortable with this piece. Dependent, initial value, growth rate, which is 1 plus the percent, raised to the independent variable, in this case the number of years since 1950. All right, make your prediction about the population this year. So this recording is in 2013, so I'll go ahead and use that. That would be year 63. So I'm going to go ahead and just write 2013, which would be year 63 according to the model. Obviously, we don't want to put 2013 in for T. So nice and easy here, everyone. In terms of our calculation and our notation there, the population for the 63rd year in the model. So let's bring that on up. Okay, so here's what I do have. Make sure I get this initial value right. You guys type it in as well, please. So I've got that times and then 1.0233, and we're going to raise that. So from my perspective, I got it to the 63rd. Boom. And we've got 5,654,000, and we'll round up to the nearest person there. How about 998? So I'll probably have to come back to that, but basically 5, something along those lines. If I missed it, so be it, but you'll go ahead and figure that out. Let me bring it up just maybe one more time, I guess. Oop, got a little dyslexia on that. So 654. Okay. Again, no huge deal, but let's go ahead and fix that piece. Okay, perfect. Could I give you any t-value and you could probably go ahead and make a prediction about the population? Sure. Okay, very nice. So what do you say we do this last piece right here? Use a graphing calculator to predict when the population could reach 6.5 million. So just according to this, population is a little over 5.5 million. When could it reach 6.5? So I hope everyone is in agreement in this case that this is the dependent variable value there. This is the y value, the population, so to speak. So theoretically, instead of putting it in for t, I've got to put it in here. So it would look something like this. Hope I've got you covered in this end, but basically this would be the equation I'm trying to solve. Times 1.0233 and raised to the t. Now at this stage, we don't have the background to solve an equation like this. Very soon over the course of this unit, we will develop the skills to go ahead and take care of this. But at this stage, unfortunately, we do not. So what we're going to do is, as it says, use a graphing calculator. And so here's how we're going to do it. We haven't really worked with this too much, but in this case, I've got a y value essentially, and I need the x. And the way I'm going to do it, everybody, is by taking the original function and putting it into the calculator. So I've got this. This is going to go into the y1. I'm going to type in my model. And then right behind it, everybody, into the y2, this also is a y value. And I'm going to plug that in. And what I'm going to do is see where I get this nice exponential graph to go ahead and hit the 6.5 million. So that's how we're going to do it off. Take care of this piece. And so I've got what I would call essentially the point of intersection between the two. And you'll see this momentarily. So jot it all down and then we'll go for it. Okay, grab that calculator. Let's take care of business. So I go to my y equals, and let's type in the beautiful model that we created here. Have that, and then times 1.0233, raise that, of course, to the x. So that is going to be the exponential model for the population of Colorado. And now what we want to do is go ahead and see where that population would hit 6.5 million. And so I tuck that into the y2. Now the only real issue here is coming up with the appropriate window. Although quite frankly, we could probably use a little foresight here and come up with some good numbers. So x represents the number of years. Obviously we start at year 0. And we're already at over 5.5 million. So after 60 plus years, so I'm going to go out 100 years. Hopefully we'll see it in that time frame. And in this case, population, obviously we could kind of start it at its beginning here at 1. I'm going to start it at 0, just kind of leave it like that. And then I'm going to leave a little buffer at the top. Essentially, I have to see where it hits 6.5 million. So I don't know, I'm going to go up to 7 million. You could do whatever you'd like here. That's the beauty of it. There's no real one size fits all by any means. But I'm going to go from 0 to 7 million on the population and cross my fingers. Here we go. Let's hit graph. So as you can see, I have this interesting exponential curve that we will explore in great detail in the near future. And then right up here is where I have my 6.5 million. And do you see there's a little intersection right there. So we go second, trace, so that calculate menu, which we've worked on quite a bit. And let's go to number 5. Intersect. Just hit enter, enter, enter. Once, twice, third time's the charm. And so you can see based on this that it looks like we would hit it in about the 69th year, give or take, so about 2019. Okay, so let's go ahead and put that together up here. I'm going to write 69.0, I missed that, which would be about 2019. And we've got it. All right. Take a look at that. If I give you an independent value, you can come up with the dependent. And now if I give you the dependent, you can come up with the independent. Wonderful. All right. Let's do one more. So example 2. China's one-child policy was implemented in 1978 with the goal of reducing China's population to 700 million by 2050. In 2000, the population was about 1.2 billion. In fact, that will be our starting value for this model. So 1.2 billion, because I think we want everything in millions here, would be 1,200 million. Suppose that China's population declines at a rate of 0.5% per year. Will this rate be sufficient to reach its goal? Okay, well, let's do the population part first. Let's just write a model and see what we gather from it. Again, what I would encourage you to do, if at all possible, is to pause the video for a second. We have an initial value right here, which we're going to, by the way, emphasize is this piece. And we have it going down by a certain percentage. So we have our percent decrease. And so we can write an exponential model as a result. So I'm going to go ahead and do mine. If you have already done it, great. If you haven't, maybe pause and see what's going on. But I have this. So the 1,200 million, so that's what the population was in 2000, where we are starting our model. And it's going down by 0.5%. Now, I'm just kind of thinking about this. Remember, 0.5%, I do want it as a decimal, so I move that 2 to the left. So 0.5% is 0.005. And I'm going to do this a couple different ways for you, just so you see. But remember, exponential decay is 1 minus the percent decrease. So if that's what it's going down by, 1 minus 0.005. And of course, because it is a constant percent decrease, it is an exponential function, and we get that right there. Now again, I would go just a slightly further and see that b value in just a little more detail. If I do 1 minus 0.005, I get that. And guys, that is a great looking model. For a value of t, I can make a prediction about the population and vice versa. Okay, well, let's see what we have going on here. It's just suppose that China's population declines. Will it be sufficient to reach its goal? So I think we were looking for this piece, 700 million by 2050. Probably a couple ways to do it, obviously. Maybe see when it hits 700 million. Would it be after 50 years or before 50 years? Or we could maybe just put in 50 right up here and see if it's above 700 million or below 700 million. I think it's easier to just throw in 50 right here. So let's go ahead and do that. P of 50. So that would mean this notation right here, raise that to the 50th. So it's going down by 0.5% per year for 50 years. And so as a result, will it hit 700 million by then or not? And let's go ahead and bring up the calculator one last time. Here we go. And so I've got 1,200 million times 0.995, raising it to the 50th. And you could see it only gets down to about 933 million, so no luck on that in terms of hitting the 700 million target. So what do we get there? Kind of missed that number again, but seem to remember something like this. You'll write it down from your calculator there, whatever you have, that's fine. And so obviously in this case, how about a big fat no? And we've got it. All right. So we took a lot of time and developed the exponential model. Get used to it, please, with growth and decay, especially that b value. And please don't hesitate to ask any questions at all. Thanks.